What's going on, guys? Welcome back to another video. Today we'll be talking about the reactions of arenes. So these arenes are aromatic hydrocarbons, and the characteristic reaction of arenes is aromatic electrophilic substitution. Within this mechanism, we have five different types of reactions. We have halogenation, Friedel-Crafts reaction, which further branch into Friedel-Crafts alkylation and acylation, and we have sulfonation followed by nitration.
So let's quickly understand the mechanism of these types of reactions. Um, we have four things to consider in this mechanism. One is a compound containing both a nucleophile and an electrophile. Second is a catalyst. Third and fourth will come in later steps. So these two react in favorable conditions to form a complex nucleophile plus catalase complex. So this is a modified catalyst. It's no longer a catalyst. It's a modified catalyst. It's called a catalase. Has a negative charge plus an electron, the free electrophile. This is the first step. The second step, we have this free electrophile, which attacks on the arene. This is the universal sign for arene, by the way. This forms the arenium ion. The third step, the arenium ion is rearranged in such a way. Of course, this arenium ion does contain a hydrogen. Is arranged in such a way that the hydrogen leaves the nuclear. This complex here breaks free, and this forms the arene and desired electrophile, and the H and U, and the catalyst is regenerated. Let's look at halogenation. It's the same mechanism. We'll take benzene as an example in everything, so it makes it quite uniform. And mostly they give benzene in exams, so you don't really have to worry about any weird molecules. If your luck is bad, then you'll get probably a benzene derivative, and if not, then no one can save you really. So you have benzene. I'm going to write all the bonds. I'm going to show all the bonds. You have Cl2. I'm going to take chlorine just for the sake of it. And chlorine exists as a diatomic molecule in nature. So I'm going to write Cl2. And this happens in the presence of a Lewis acid, FeCl3. And it happens in dark because we don't want the chlorine breaking homolytically. So this will form our chlorobenzene and our HCl mechanism. Of course, the Cl2 oh, reacts with FeCl3 in the dark to form the FeCl4 minus complex and the chloronium ion. This is your attacking electrophile. This is your nucleophile catalase complex. Now, this chlorine in the second step, this is 1, this is 2. The second step, this chloronium, sorry, this is chloronium, but this is important to remember. Whenever you have a negative charge, it's chloride, and when you have a positive charge, it's chloronium. So, ium ide. So, chloronium will attack on our benzene. Of course, benzene has a hydrogen because it has a molecular formula C6H6. So, in the next step, what happens is that this pi bond transfers here, and there's a vacancy created here. Now, this is the arenium ion that I talked about earlier. This is the arenium ion. Also, this is not there. It just came out as force of habit. Then this is a very unstable species. This is actually a reaction intermediate that doesn't last for very long. This rearranges in such a way that this hydrogen leaves, this pi bond transfers back here, this forms chlorobenzene as we know it, and a free proton. Now this free proton will go and attack that complex we mentioned earlier, FeCl4. It will liberate that one chlorine and it will form HCl, and FeCl3 will be regenerated. That's halogenation for you. This happens in bromination, iodination, chlorination. The only thing you have to remember is that whatever catalyst you choose has to have the same reagent. So if I choose, if I want to chlorinate something, I'll have something that has, if like for example, FeCl3, AlCl3, or something along the lines that contains my attacking reagent. And if I have bromine, I'll use FeBr3 or something like that. Iodination, I'll use something like aluminum iodide, although that's very unstable. I don't think that exists. So yeah, that's it for halogenation. The next step, the next reaction I'll have is Friedel-Crafts alkylation. So Friedel-Crafts alkylation, same reaction, except there is one difference here. Friedel-Crafts alkylation. Mechanism goes the same way. I'm going to use benzene as my arene everywhere, so it makes it easy. Benzene, this is the general reaction. This can also be benzene, that is also benzene, it's both the same. Plus Rx, alkyl halide. This is your reagent. The presence of Lewis acid. So you don't need to worry about the dark in this reaction because there's no homolytic fission. If Lewis acid, like it's a name reaction, so we have to follow the catalyst given. It's anhydrous aluminium chloride, and this forms your benzene derivative and HX. Now, mechanism again. Benzene. I'm going to use chlorine, huh? Just for the sake. You can use bromine, you'll have to change it to AlBr3, aluminium bromide. I'm going to use R as C2H by ethyl group or methyl group, CH3. I'm going to make toluene. And AlCl3. So The reason we use this aluminium chloride is to perform a heterolytic fission here. We want a carbocation to be formed. We have a methyl carbocation, which as we all know is very unstable, followed by chloride ion, which will attack on the which will attack on the catalyst to form the nucleophile catalyst complex, AlCl3. This will form AlCl4 complex. That's your first step. Your second step will be this attack here. So we have benzene. I'm going to write all the bonds because I'm going to need to show you all the bonds. The positive charge. This is a carbocation. This will react. This pi bond transfers again here. This forms, and after this pi bond transfers, this attacks here. This forms a vacancy here. Of course, bonds still exist here and here. And there is a methyl group here. Now, this hydrogen, this is your rhenium ion again. What happens next is this rhenium ion rearranges itself. The hydrogen leaves. Uh, that pi bond transfers here, and this forms toluene and the proton, which goes on to attack, oh, which goes on to attack on the nucleophile catalase. I use aluminum chloride, right? And this liberates AlCl3 as it is and HCl. That's Friedel-Crafts alkylation for you. And let's try a reaction by yourself. Let's try the reaction. Let's try benzene plus, let's see, what does this give? I'm going to wait a second. You can pause the video. You can answer. Of course, the answer is ethyl benzene, undoubtedly. Plus HCl. Now, for this reaction to happen, you have to consider the most stable carbocation. Now, you may ask, what's the most stable carbocation? I will make a video on it later because it's a very big topic in itself. So for now, I'm just gonna stick to these basic carbocations which require no rearrangement whatsoever. And that's Friedel-Crafts calculation for you. The next step, Friedel-Crafts acylation. Friedel-Crafts acylation. So Friedel-Crafts acylation is not really much different than Friedel-Crafts alkylation. You have an arene, benzene. You have some acyl halide. You react it in anhydrous aluminium chloride. We'll use aluminium chloride, acyl chloride, of course. Anhydrous aluminium chloride. And you get a ketone and hydrochloric acid, of course. Same mechanism as previously mentioned. You start with benzene. Start with benzene. You lay out your materials. Your catalyst comes in. Your catalyst homolytically breaks your attacking reagent, forms a carbocation and a chloride ion. Get Cl minus. We have R C double bond O plus, which is a resonance stabilized carbocation. This is resonance stabilized species. And you have benzene as itself on the side bench, wondering when its turn will come. Okay, so now benzene, full bonds will be shown. I'm going to add the hydrogen too, because why not? We'll have the carbocation. Of course. We'll have the same pi bond transfer that occurred before. We'll have the same attack. Of course, remember the carbon always attacks. The electron deficient carbon always attacks. I'll write it here. We will be formed with the arenium ion. And of course, there's a vacancy here. This arenium ion will last for a little bit more because it's much more resonance stabilized, but not as much as we expect it to be. This will break down to form your end product, which is your ketone, your aromatic ketone. And then the hydrogen will attack your nucleophile catalase complex that you have made. Of course, oh yeah, this goes on and attacks AlCl3 to form AlCl4 minus. This step is common everywhere. In every aromatic electrophilic substitution reaction, you will see this. Also, ARS, aromatic electrophilic substitution is too long to say. I'm going to say ARSC. ARSC is aromatic electrophilic substitution. So in every ARSC, you will see this step. You see this step here, and you will see this step here. This proton coming out and hitting that nucleophile catalase complex, liberating that fluoride, forming HCl. This is the end of this reaction. So
Sulfonation basically means adding a sulfonic acid group to an arene. This is another aromatic electrophilic substitution reaction. So sulfonation, adding the SO3H group, which is the sulfonic acid group. the sulfonic acid. So general mechanism, then reaction, benzene, fuming H2SO4, reacts to form benzene sulfonic acid, and water. Mechanism would be such that benzene, I'm going to draw out the hydrogens just in case, plus H2SO4, HOSO3H. This is another way to write it. In the presence of some Lewis acid catalyst, this would be again sulfuric acid itself, excess sulfuric acid. This breaks to form a hydroxide ion and the sulfonium ion. So we have OH minus SO3H, the positive charge, and we have benzene sitting right there. The next step, we'll have the electrophilic attack. This is our electrophile, brother. This is the attacking electrophile. The next step, benzene. I'm going to write out all the bonds for now. H plus SO3H plus. This goes on, attacks here, and this pi bond is technically supposed to shift here. This is the first step, this is the second step. This forms, again this forms your arenium ion, which is an unstable species. Forms a carbocation. And this is your arenium ion. This arenium ion will be this arenium ion will be rearranged in such a way that we will lose this hydrogen, this pi bond transfers back, and we will get benzene sulfonic acid as it is, with a water byproduct. As that single H will attack, that proton will go and attack the hydroxide. This forms H2. And now we have nitration. The next step. This is sulfonation is done. Second last reaction, nitration. Now this is where things get a little complicated. Benzene, of course, nitric acid, in the presence of sulfuric acid. Forms nitrobenzene. And sulfuric acid works as your catalyst. Now, an important thing to remember here is that sulfuric acid and nitric acid are when used together, are known as something called the nitrating mixture. Of course, this is concentrated. concentrated sulfuric acid, concentrated nitric acid. So this reacts in this manner, since that HONO2, this is nitric acid, you can count whatever elements I'm laying. Sulfuric acid. So in the presence of this sulfuric acid, this nitronium ion is made. And oh, I forgot, this is not written this way in this reaction. A bisulfate ion is made, or a hydrogen sulfate ion. So let's go just write down all the ions we have. We have nitronium, we have hydroxide, we have a proton, and we have bisulfate. Right. So in the next step, we have benzene, an old friend, going about its day as usual, until it is attacked by a nitronium ion. Now the nitronium ion is the attacking electrophile in this case. Okay, so this is the attacking electrophile. Of course, pi bond transfer happens again. Nitronium attacks again. In the next step, we have your arenium ion again. We have your hydrogen. We have a carbocation here, and we have the two bonds intact. Now, we need a base to neutralize this acidic product. This product is really acidic. So, of course, as we know, we have a base here that can neutralize this product. So that's going to work. It's magic. We're going to get nitrobenzene. These two will form water. That's the end of all your aromatic electrophilic substitution reactions for hydrocarbons. If you enjoyed this video, please do like and do subscribe so I can know what type of content to post further. Also, do follow our Instagram, which is in the description below, and see you in the next time.